Good morning, ladies and gentlemen. I'm honored to have the chance to speak at this conference. I'm a postgraduate student from Harbin Engineering University and currently doing some research on life prediction of marine concrete. Today, my topic is service life prediction of concrete structures under chloride environment based on Monte Carlo method. The content of this presentation is divided into 4 parts. In Section 1, I will introduce the background of corrosion of marine concrete and some existing methods for predicting the surface life. In Section 2, I will propose a prediction method based on Monte Carlo method and compare it with the literature. The mathematical model considering the 2 kinds of activation energy values and simulation results will be shown in Section 3. And finally, I will make a conclusion. Marine environment is a complex and harsh natural corrosive environment. The corrosion of marine concrete structure is very serious at home and abroad. Moreover, the cost of maintenance and reinforcement of the structure is much higher than the construction cost. So, it is necessary to predict the service life of concrete structures. Most service life prediction models take the corrosion initiation period as the dominant factor, determining concrete service. Existing predicting methods fall into 2 main types: deterministic method and uncertain method, as shown in the table. The most popular approach today is to combine mathematical models with random method. Monte Carlo method is often used for random simulation of parameters to predict the service life. Some investigations have proposed a distribution variables approach and got a good effect. It is well known that temperature has an effect on chloride diffusion. Arrhenius law is usually employed to describe the correlation between chloride diffusivity and temperature. About the value of activation energy in Arrhenius law, there is no universal method. The value in investigations or prediction models are specified in the following table, and most of which are constant values. But many researches have shown that the activation energy varies with the diffusivity of concrete. Based on the analysis of RCM test results, Liu developed the correlation between no steady-state migration coefficient at 21 degrees Celsius and activation energy, as shown in the figure. To sum up, the objectives of this study are as follows. One is to use Monte Carlo method to predict the service life and compare with distribution variables approach. The other one is to explore the influence of the value of activation energy on the service life prediction. Model setting is based on fixed second law. When the chloride concentration reaches the threshold, the steel is considered to be corroded. The service life can be expressed as follows. Distribution variables approach is based on the idea of finite element. The probability of structural failure is obtained by comparing the damaged elements with the total elements. But Monte Carlo method calculates and records the probability of service life at each time point through random sampling. The process is shown in the figure. According to the literature, the parameters of a bridge are shown in the table below. The service life of this bridge is predicted by using the above two methods. The predicted results are shown in the figure. It indicates that the predicted results from Monte Carlo method are basically consistent with the distributed variables approach. The activation energy value of Life 365 model and the relationship between no steady-state migration coefficient at 21 degrees Celsius and activation energy obtained by Liu test were selected. Considering the relationship between activation energy and migration coefficient, the statistical model can be written as follows. Taking the Hong Kong-Zhuhai-Macau Bridge project as an example to predict the service life of concrete structure in splash zones at different temperatures. A summary variables for the model are listed in the table below. The reference temperature is assumed to be 21 degrees Celsius. 5 degrees Celsius is taken as an interval to take values range from 10 degrees Celsius to 35 degrees Celsius. The picture shows comparisons of damage probability under different temperature in two kinds of activation energy value methods. We can see from the picture that the service life is shortened with the increasing temperature, but when the probability is the same, the prediction time of the two models is different at the same temperature. The comparison of probability changes at different temperatures are shown in the next few figures. 5% is assumed to be the maximum probability that concrete structures are allowed to reach the threshold within time t. We can see from these pictures that when temperature is less than 20 degrees Celsius, the time gap between two models to reach the probability limit reduces with the rise of temperature. The predicted results are basically the same at a certain temperature between 20 degrees Celsius and 25 degrees Celsius. The time gap reduces first and then increases with increasing temperature. This is because the activation energy value at various temperatures calculated by the test formula differ from that in Life 365 model, which results in a large difference between the mean value and standard deviation of chloride diffusion coefficient, calculated by Arrhenius equation. This illustrates that the temperature sensitivity of this model is greater than that of Life 365 model. To sum up, the results predicted by Monte Carlo method fit well with those predicted by distributed variables approach. There is a difference between the service life by the model in the paper and the Life 365 model. The correlation between migration coefficient and activation energy might provide a reference for the durability design. That's all. Thank you.